Section 2.2, we're going to look a lot at graphing. And we're going to continue our discussion of domain and range and functions that we talked about in 2.1. And we're going to add one additional piece of information onto that. For starters, we're going to be looking at 7 basic graphs. We're going to be looking at the same information for all the basic graphs, namely, is it a function? What's its domain and range? And then what do we have in terms of the graph increasing, decreasing, or being constant? So we're going to look at those same features for every single graph. The graphs are ones that are considered basic graphs. Some of them you might be very familiar with, others maybe less familiar with. This one is one that you probably are familiar with, y equal x squared. What does this graph look like? Shape-wise, any ideas? Right. Do you know what that's called or how you would describe that? It's a parabola, yeah. Sometimes people describe it as having the shape of a U. So you're right, the basic graph looks something like this. And we're going to talk later about what do you do when you don't have graphs that you know the basic shape of. For most of these that I'm going to give you here at the beginning, I'm going to just give you the shape. But this is the shape of the parabola, or of a parabola, or the graph of y equal x squared. So thinking about this graph, first of all, there's no place for us to note it, but we're going to do it on all of the problems. Is this a function? Yes. So remember, we can determine a function if a graph is a function by the vertical line test. Simply drop the lines down. If it crosses it twice, it's not a function. This one it doesn't, so this one, yes, it is a function. So looking at that then, we would talk about what is the domain and what is the range. Now you can do the domain and range whether it's a function or not, all right? It's going to exist either way. The other components, not necessarily so. So let's actually talk about this. Remember that we talked last time about domain being what happens along the x-axis and range being what's happening along the y-axis. So if you're talking about the domain, you're talking about walking, if you will, along the x-axis from the left to the right, and you're looking up and you're looking down. And as you do that, moving from left to right, where are the first places in terms of the x values that you see part of your graph? Right. It starts on the very far left, which is represented by the quantity negative infinity. As I look up, I see a value. And as I keep going and looking up and down, walking all along the x-axis, I never stop seeing values. There's part of my graph everywhere, so it continues on to infinity. After I look at the x-axis, I climb up along the y-axis. So now I'm climbing like a ladder, and I'm climbing up, right? So he's walking over this way. He's climbing up, but as he's climbing up, he's looking to the left and to the right. So his head's going like this, be-bopping back and forth, okay? But he's climbing up. And as he does that, what is the first location in terms of the y values that he sees part of the graph? Yeah, at 0. That's where it starts. And it actually equals 0, so we use a bracket. And then as we keep climbing up, where do we stop seeing y values? And Amara, you told me. Yeah, we actually never stop seeing them, so we represent that quantity as infinity. Okay, is that okay so far? So we're going to do this idea of domain and range on every single problem. The other thing we're going to do, and this is a new idea, is that we're going to talk again about moving along the x-axis. So again, we're focusing back on our little guy right here. And we're going to imagine instead of him being on the axis, he's actually on the graph. So he starts on the graph on the far left. So here he is up here on the top. And again, he's moving, to the right-hand side. He's moving from left to right. And the question we want to ask ourselves is, what is the graph doing? Is he going downhill from left to right? Is he going uphill, or is he on a constant flat piece? So we're not going to see the constant flat pieces for quite a while here. It's the very end of the lesson where we finally encounter one. But initially on this graph, what's he doing? Is he going down or is he going up? He's going down. He's sliding down the curve, right? That's a decreasing part of our curve. And how long is he? Well, he starts decreasing. on the far left, represented by negative infinity. When does he stop decreasing? Yeah, when he gets to 0. Now, our book tends to use parentheses on everything for increasing and decreasing pieces. And I think that's what makes the most sense. We don't increase or decrease at a specific point. We actually might even change whether we're increasing or decreasing at a specific point. We always increase or decrease over an interval. So it says over the interval from negative infinity to 0. We don't do it at a specific point, so we use parentheses. It's kind of nice. It makes it easier to determine. At 0, however, what starts happening, as our guy gets to 0, he goes back uphill after that. And so he is going to be increasing. And where will he stop increasing? Never. So that's represented as the quantity infinity. Okay, so this is the process we're going to use for all 7 of the basic graphs that we're going to encounter, and this was the first one. Elisha? Say it again. Yeah, so again, when we use a bracket, we mean that we're actually doing something at a specific point. It equals the point. We're going to use parentheses, and the reason that we are is because it doesn't really make sense to talk about what's happening at a specific point. For example, at this point right here, it's actually changing. It's decreasing, and then it's increasing, so where do we include it? It doesn't really make sense to include it in either one, because it's not doing anything at that specific point. It's actually changing directions. So using parentheses is what makes the most sense so that it doesn't get included in either the increasing or the decreasing portion. Okay? All right, we're going to try some more. Our next basic graph is y equals x squared. This one's maybe less familiar to you. It's something that we've already encountered back in section 2.1, as in the basic shape of it. But it looks like this. It actually looks like sort of half of a parabola sort of fallen over on its side. So as we're looking at this, first question, is it a function?
Yes.
Yes, it is. Passes the vertical line test. Why are we actually asking ourselves whether it's a function? Well, to be honest, when we encounter the first one that's not a function, we have to do less work. And I'll show you when we get there what I mean. It is a function. Either way, it has domain and range. So as we're moving along the x-axis from the left to the right, where do we first see domain values or x values? Yeah, at 0. And we see them at the value of 0. As we continue to move to the right, where do we end? Never. So it's infinity. So my domain is negative infinity, or I'm sorry, is 0 to infinity. Now, range, climbing up the y-axis. Where do we first start seeing y values? 0 again, right? Y equals 0 is our first y value. Where do our y values stop? They never do. Now, they aren't near as quickly increasing, right? This part of the graph continues to go up, not very fast, not like the last one, but it does continue to go up. So it never has an ending point on the y values. Okay, so again, when we're talking about increasing, decreasing, and constant, we're talking again about moving from left to right. But we're moving from left to right sort of along our curve. So as we're moving from left to right, are we going uphill, downhill, or staying flat? Going up, so that's an increasing graph. And this one actually is increasing at 0. If you did, it wouldn't hurt anything because there's nothing before it, but instead it kind of changes direction there. So we're going to just, honestly, if you'll just use parentheses everywhere on your increasing, decreasing, constant, that's going to be fine. Where does it stop increasing? It doesn't. It continues to increase for the whole graph, infinity. When it says decreasing and it says constant, there aren't any. There are no places on this graph where we're going downhill, no places on this graph where we are flat. Is that all right? It's quite likely that the third one is not a familiar graph to you. It's x equal y squared. It actually looks like this, which you might describe as a sideways parabola. And that would be a pretty accurate description. It is not a function, you're right. So why does that matter to us? Well, catch this. If it's not a function, we cannot talk about increasing, decreasing, and constant. Because we can't move from left to right along one single path. I would somehow have to be moving along this path on top that's increasing, and this graph on bottom that's decreasing at the same time, and that doesn't make sense, right? I can't move from left to right, I'd have to pick a path. So there's simply not a way, in fact, you know what, let me just leave the little guys, the little blue guys on there. There's not a way to talk about increasing, decreasing, and constant if it fails to be a function to begin with. So when you fail to have a function, you don't even have to do as much work because you don't have to talk about it increasing or decreasing or constant. You do still have, however, a domain and range. The domain and range exist whether you have a function or not. So domain means moving from left to right, and as I move from left to right along the x-axis and I look up and down, what is the first x value where I see part of my graph? 0. And where do I stop seeing my graph? Infinity or never, meaning infinity, right? Range, climbing up my y-axis. Where do I start seeing values? Negative infinity immediately. And where do I stop? Infinity. It continues on forever. I want to show you something cool. Are you ready? Look at the domain and range on number 3 compared to the domain and range on number 1. What do you notice? They're switched. There's actually a reason for that. Look at the equations. Y equal x squared, x equal y squared. What can you tell me about x and y? They're switched. So if domain means the x values and range means the y values, and I switch x and y, it automatically happens that I switch my domain and my range. We'll come back to that idea later on, but I wanted to show it to you here because this is the first time we've encountered it. All right, let's talk about another graph. We're going to do y equals x cubed, and this graph looks something like this. It's not perfect, but it's good enough for the purposes of what we're doing. Is it a function? Yes. Okay, domain. Moving from left to right, what is your first x value? Where do you start seeing them? Negative infinity, you immediately have them all the way to the far left. And where do they stop? Infinity to the far right. How about my range? Moving from the bottom up, climbing along the y-axis. Same thing. Okay, moving from left to right, increasing, decreasing, constant. What's happening? It's increasing the whole time, right? Yeah. Now, I may be doing it faster at some places and slower at some places, but I'm still going uphill the whole time. Those of you who have ever run hills knows those hills that are really gradual, and you know the hills that are really steep, but you're still going uphill, right? So we are increasing from negative infinity to infinity. Again, there are no places that are decreasing or constant on this one. Yes? Because we're still moving from left to right. So even though we're not going uphill maybe as fast, we still, moving from left to right, are still in an upward trajectory. Any other questions? Okay, so we did y equal x cubed. Now we're going to do y equal the cube root of x. That graph looks approximately like this. Is it a function?
Yes.
Yes. What's its domain? Negative infinity to infinity. What's its range? Yes. Since it's a function, we have to answer the questions increasing, decreasing, or constant. What's it doing? It's increasing. Where? The whole time. Now, it's not increasing the same way the last one was, right? The last one was really steep increasing. Nobody wants to climb those hills. All right, this one's much more gradual. It's steep kind of in the middle a little bit, but it's much more gradual, but it still is increasing as we move from left to right the whole time. So no places for decreasing and no places for constant. All right, the next graph is a little different. The equation feels funny. You've actually seen this equation before. You saw it in the form of x squared plus y squared equals r squared. So like if you were to square both sides of this thing, it would eliminate the plus or minus in the radical. And we could shift the x squared to the other side. This is actually the equation of a circle. Either of these forms are. Let me draw it in here and then shift it to the right location. So it looks something like this. What you'll notice is that the radius is r, so it goes to the left, to the right r. It goes up r. That was bad. Let's try that again. What do I do about the going left and down? It's a distance of r, right? But over here, it would hit at negative r because I go a distance of r out in all the directions. And over here, I would hit at a negative r because I would have gone r left and r right, r up and r down. Okay, does that make sense, visually speaking, with the positive and the negative r's that I've written in? Because the equation tells us so. R is the radius. So if it said a specific number, we'd have a number to put in there, but we don't have a number. Just have a general R. Is it a function? No. All right, still we can talk about domain and range, but we kind of don't have to do near as much on this one because we don't have to do increasing, decreasing, or constant. So what is the domain if we're moving from left to right? What is our domain for our circle? Yeah, so negative r to r. We do include them, right? There's not like unboundedness. It actually equals those corners from the left to the right. What's my range? Yeah, negative r to r, same thing. And if I did have numbers, I would be able to use them in there. That would be fine, right? If it was a radius of 5, we'd go negative 5 to 5, negative 5 to 5. That'd be fine for whatever it was. Okay, so yay for not being a function. Less to identify, right? Does anybody remember what an absolute value graph looks like? Some of you are throwing your hands up in the air. Kind of looks like a parabola, but it's not a U, it's a V shape, yeah. So it looks something like this. Yeah, that's pretty close anyway. Yeah, that's an absolute value graph. What's the domain? Yeah. Negative infinity to infinity, it's my domain. What's my range? 0, which we get to equal to infinity. I didn't ask, I should have, I'm sorry, when we started. Is it a function? Yep. it is, which means we are going to answer the questions about increasing, decreasing, and constant. So if we start on the far left and we start moving, are we going to be increasing, decreasing, or constant? Decreasing. So the far left is the value negative infinity. When do we stop decreasing? At 0. And again, our intervals are going to include parentheses. What happens after 0? It's increasing. So it's increasing from 0 to infinity. This one still had no places where it was constant. Okay, everybody good so far? Okay, that puts us at number 7. I told you there were 7 basic graphs. Those are the 7. What we're going to do next then is to talk about what happens if it's not one of those basic graphs and how we'll be able to use the same types of tools that we were using in terms of domain, range, increasing, decreasing, constant to make our decisions. So we're going to start now with graphs that don't have one of those basic forms like exactly and figure out what to do. So there's lots of ways to graph. So what I'm going to show you is not the only way. If you use another reasonable way to do so, which does not mean put it into your calculator. It means a reasonable way to do so. So does anybody know what this equation is an equation of? What's the shape of this equation? This is not a trick question, I promise.
Is it a line?
It's a line.
Okay, cool.
This is an equation of a line. For a lot of what we're doing, whether we know what the equation is or not, we are able to plot points to make some determinations. So even if you looked at this and you're like, not 100% sure, we're going to be able to plot some points. So we're going to start with plotting some of those points, and we're going to do it by just identifying some x and y values. There are often x and y values that are nice to choose, and you can usually identify them simply by looking at whatever the equation is you have. For example, what might be a nice value to choose here for x? 0 might be nice. If x is 0, what would y have to be to satisfy this equation? 0 as well. So that's great. We got one plot. We can plot the number 0, 0. Easy peasy. Give me another value for x that you might like to use. 1 would be nice. If x is 1, what's y? It also works at 1. So the point 1, 1 is on my graph. Let's actually go to the left-hand side just for the sake of having tried something that's negative. Somebody give me a negative x value. All right, negative 1 will work. And if x is negative 1, what's y? It's actually negative 1 as well. And if you weren't sure, you could actually plug it in physically and see. So, sorry about that. By putting x as negative 1 and solve for y, right? So I have negative 1, negative 1. It is a line, right? So it looks something like this. What's the domain of this graph? Yeah, negative infinity to infinity. What's the range? Yep. Increasing, decreasing, constant. Yep, it's increasing the whole time, right? Just like that. The next one's a little bit more interesting of an equation. Do you know what the basic shape should look like overall? A V, right? It's an absolute value graph, so it should look like a V. Now, it's not going to look exactly the same as this one because there's other numbers that are going on with this, right? So it might be shifted left, right, up and down, expanded, collapsed, flipped upside down, but it's going to have some sort of a V shape to it. Does that make sense? Okay. Now, in order to get the V shape properly done, we do need to be a little bit more careful than we had to be on the last one on how to choose points. In particular, I would like to choose points that both give me a positive, a negative, and a 0 inside of my absolute value. Let's start with the 0. What would x have to be so that what's inside of my absolute value is 0? -1. If x is -1 and we put a -1 in right here, I will get 0 inside my absolute value, right? That's a valuable point to plot. So if I get 0 inside my absolute value, what's the absolute value of 0? 0. And what's the opposite or negative 0? 0, right? So this is one of my ordered pairs that I really do want. I also need an ordered pair that plops out as a positive inside of my absolute value. So what x value could I pick so that inside my absolute value I get a positive? What's that? X could be 3. X could be 1. X could be 0. You have lots of options. You just need to pick something that makes the absolute value positive, okay? If x is 3, 3 plus 1 is 4. The absolute value of 4 is 4. And then the negative in front makes it the -4. You just were a step ahead. So I'm finding what happens when I plug in x equal 3. Now I need to choose a value for x so that the absolute value inside of it is negative. What could you pick for x? -2. That'd work. Lots of options again. -2 would work. What's -2 plus 1? -1. What's the absolute value of -1? 1. And the number in front being negative also flips the sign then to be -1. So we do end up with a -1 at the end, but not because of the absolute value, but because of the negative out here, right? So the absolute value flips it to positive. Okay, this, along with the fact that we're expecting a V shape somewhere, is enough to graph this. So we're going to plot these points. I have -1, 0. That's this. I have 3, -4. Oops. And I have -2, -1. So this V is going to be shaped opening downward, right? And we'll talk more about that negative on the outside and how that's sort of coming into play here. But this shape looks like this.
Oh, yeah. Okay.
Is everybody good with that? That's how those dots would connect, knowing that it's a V shape and then connecting those dots. Lovely. What's the domain? -infinity to infinity, right?
Oh,
Yeah.
yeah.
Yeah, you're still thinking about y values. So we're still moving left to right. -infinity on the left-hand side of the x-axis, +infinity on the right-hand side of the x-axis. What's my range? Okay, so climbing up, -infinity to 0, and I can equal 0, so I do need a bracket. I didn't ask, I should have. Is it a function?
Yes.
Yep, it is. So we do have to answer the increasing, decreasing, constant questions. As I'm moving from left to right, what is my graph doing initially?
What's the increase?
Yeah, it's increasing. So this is the most interesting one that we've seen so far in terms of increasing. Where does it start increasing?
-infinity to 0.
Okay, it's -infinity, but it doesn't stop increasing at 0. Where does it stop increasing? At -1. How did you get -1, Jonathan?
Oh, okay.
That's where that
Right, and by point, you're actually talking about the x-coordinate of that point, right? Okay, so we want to be really careful to remember, because this is the most interesting one we've seen since they don't correspond to the origin, right? We actually are reporting this in terms of the x value. So as my little guy is going uphill, the x value he stops at is actually -1. So that's where my x, reporting of the interval for my increasing will end is at -1. So after -1, what happens?
It decreases.
Yep, it decreases until we get to to positive infinity. I know, right? Remember our x values we're reporting, so it's positive infinity because it's on the right-hand side, and I have nothing in terms of the constantness of it. Okay, so I feel like we really need to see one that has something that's got constant piece, don't you think? Because so far you've written none on every single one. So let's do an example now. This is a little different, feels like it at least. Instead of starting you out with an equation like the other two did, we're going to start you out with it would be like a slightly different direction set in your homework where it actually starts you out with a picture graph, okay? So we're going to just simply start this one out with a graph, and it's not going to have an equation. The graph looks like this. Okay, so there's no equation to deal with. It's just a graph given to you. First, is it a function? Yes. Sorry, let me pause just a second. You have to draw the graph in this time since I did it. I'm sorry. What's the domain? Yep, negative infinity to positive infinity. What's the range? It's negative infinity to something. To 3. Yeah, so as I'm climbing up at this spot right here, right? A little bit below it, but so that I can distinguish it. I stop seeing y values. From then on up, there's no more graph. So it stops at a y value of 3. Moving from left to right, what is the graph initially doing?
It's increasing.
It is increasing. So it starts out negative infinity, it's increasing. Until when? Nope.
No. 2.
Close.
Negative 2.
Negative 2. So the graph stops increasing at this corner, right? And the x value of the corner is what I report. The x value of that corner is negative 2. So it stops increasing at negative 2. What happens after negative 2?
It's constant.
Told you we're going to have a constant one, right? It's actually flat. It's constant from negative 2 to where?
Positive.
Positive 2, you betcha. And then what happens at positive 2?
It decreases.
Starts to decrease until infinity, right? X value infinity. Infinity. Okay, got another one that I'm going to graph for you. It'll take me a minute to graph it though, so don't sketch anything. Otherwise, you're going to end up having to sketch it and rewrite it because the way I have to draw it to get it to look right. Okay, that's the graph. Is it a function? Yes, passes the vertical line test. What's its domain?
It's negative 1.
So we're starting from the far left.
Negative 3 to
And the x value where we first start seeing things, you're right, Amari, is -3. Okay, so -3 is our first x value. And where do we stop seeing x values? Infinity, right? Yes, thank you. I didn't get that in there right. Bracket. How about our range? Start at the bottom, climb up. Reporting y values. -1. Okay, so we report y values when we report range. It's the only one we report y values for. It starts at -1. Where do we stop having y values? 2. Yeah, very interesting graph, far more so than the others. What about the increasing, decreasing, so forth? We start on the far left, so it means we're starting at the x value of -3. What's it doing?
It's increasing from -3 to 2.
Okay, so it's increasing from -3 to 0. So I know it's tricky. So we're reporting x values when we're moving from left to right. Starts at -3, stops at 0.
I think it's decreasing from 0 to 3.
Decreases from 0 to 3, right? It's on the sloping down part of that sort of semicircle. And then
It's
constant from 3 to infinity. This is our winner so far at being most interesting graph, agreed? Yeah, it has all the features, didn't it? None of the others had this so far. All right, the last two I'm going to hurry through because we do just have 5 minutes. But I'm actually going to talk about real quick what happens when you're given a graph that's defined piecewise. So when you're given a graph that's defined as a piecewise function, you need to pick values on each of the pieces. So what do I mean by piecewise? Well, this piece says that x is less than 0, and this piece says that x is greater than or equal to 0. So I need to make sure I pick values in both of those areas of the graph. Now, these are square root graphs. But I need to pick values in my x, y's that are both less than 0, so something like maybe -1, and greater than 0, something like 1. And then I actually need to pick what happens as well at the sort of edge. What happens at 0? So I'm going to write down 0. I'm going to write down 0, and I'm going to write down an approximately 0. And I know that feels funny, and it's going to not even make sense on this particular problem, but I need it in the next problem so you can see the difference. So if x is -1, then I'm in this part of the graph. And the reason I am is because -1 is less than 0. So I'm plugging -1 into this equation. So if I plug in -1, I have the absolute value and the negative of -1. There's two negatives there because I'm in the first equation. I'm in the first equation because -1's less than 0. The opposite of -1, or negative and negative, is a positive, and the square root of 1 is 1. So I get the ordered pair -1, 1. We'll get there in a minute. It's approximately, but we'll get there in a minute. Kind of. Let's see. So the next one is x is equal to +1. Well, x is equal to +1 means x is greater than 0. So we're going to put it into this equation because that's the equation we're supposed to use if I pick values greater than 0. So I have the square root of 1, which is also 1. So now I have the point 1, 1. Don't connect them. Got more to do. But that's what I have so far. If x is actually equal to 0, which of the two equations am I supposed to be in? The top one or the bottom one? The bottom one. So that's where I'm really supposed to be if x is really 0, right? And the square root of 0 is 0, so my ordered pair is 0, 0. Now, the reality is on this one that the graph meets up at 0. We're going to see that that doesn't always happen on my next example. But if I were to put 0 in up here, what would happen? What do we understand -0 to mean? What does it mean?
It's 0.
It's just 0.
Okay.
And what's the square root of 0?
0.
0. We get the same thing, right? So if we were to accidentally plug this one, 0, into the wrong equation, I'd get the same thing. So what does that mean? Well, it actually means that as I'm looking at the left-hand side of the graph, which looks like this, and as I'm looking at the right-hand side of the graph, they actually meet at that sort of divot in the middle. So this kind of looks like a bird. Let's do the graph information real quick so I can show you why this changes on the next equation. Is it a function? Yes. What's the domain?
We use negative infinity to 0, or yeah.
Goes all the way from the far left to the far right, so it's negative infinity to infinity. The range, moving from the bottom up, starts at 0 and infinity. As I'm moving from left to right, initially it is decreasing. It decreases until I hit until I hit the origin, so negative infinity to 0. And then from 0 to infinity, it's increasing. So this one's constant nowhere. The next piecewise part is a little more interesting, so that's the one I wanted to show you as well. We're still going to pick two x values in each area of the graph. So I need that t-chart, or that number ordered pair chart. I need to pick x values that surround the number, in this case 2. So I'm going to pick the numbers bigger than 2, so maybe I pick like 3, right? And I'm going to pick a number smaller than 2, so maybe I pick, like 1. It doesn't really matter. I just pick something bigger than 2 and smaller than 2. And then I also need to pick 2 and approximately 2, and you'll see why here it's different. So, if I pick the value of 3, am I in the top equation or in the bottom equation? The bottom. If I pick 3, 3 is bigger than 2, so I'm here. 3 plus 1 is 4. So I have a point. 1, 2, 3, 1, 2, 3, 4. If I pick the value of 1, I'm in the top equation. If I put 1 in here, I actually get 1.5. So at 1, I'm sorry, not 1.5, 0.5. So at 1, I'm at 0.5. If I pick 2, which equation am I in, top or bottom? Yeah, I'm in the top one. And if I plug 2 in here, I will actually get the number, what? -1 is right. So 2, -1 is actually on my curve, or on my graph. Here's what happens when I'm talking about approximately 2, when they don't meet up. If I plug 2 into the other equation, what do I get? 3. That is not the same number, right? Last time it was, this time it's not. So what does it mean? It means at that location where I'm not really able to do that, I get a hole. So there is a hole at 2, 3, right here. So these are the values that were bigger than 3. And these are the values, and if you wanted to, you could plot more points to verify to yourself, are smaller than 3. This graph doesn't meet up at the corner like the last one did. Is it a function?
No.
Yes. The only potentially overlapping point is right here. And it doesn't overlap
Oh, I guess they're two separate. Okay.
because one's an open circle and the other one's closed. So it's a function. The domain, again, is negative infinity to infinity. I'm super close. The range is actually, let's see, down there at -1, which is a bracket, to infinity. It is decreasing from negative infinity to the value of 2, increasing from 2 to infinity, and constant nowhere. Definitely a different kind of graph. So while you're packing up, just keep your ears open real clearly. Homework for 2.1, 2.2. That's the first thing, okay? That means that your quiz is pushed to Thursday, so there's no quiz. Secondly, I won't be here next week. So you're going to have videos posted, you're going to have videos to watch, things to upload, and so forth. As you have questions, send me emails, go to the Success Center, and so forth. That means that your quiz, which will be on Thursday, will be done like we did the quizzes before. I'll send you an email at the exact start time of class. Exactly 15 minutes later, it needs to be uploaded for credit. Okay? So don't push that limit. Make sure that it really gets uploaded. If you have any questions, let me know, and you'll get an email with those details as well. Have a great week.